Let's study power generation plants. We will first start with thermal power plant.
This looks complicated, doesn't it? Don't worry, we're going to follow 3 simple journeys and discover how this entire thermal power plant produces electricity.
The basic idea is simple. Chemical energy in coal becomes heat, heat produces turbine, and the generator converts that mechanical energy into electricity.
Our first journey begins with coal. Coal is stored at the plant before being transported to the coal handling system.
The coal handling plant transports, processes, and feeds the coal toward the boiler. The goal is to supply the furnace with fuel continuously. The coal finally reaches the boiler, where it burns with air. Its chemical energy is released as a huge amount of thermal energy.
Combustion needs oxygen, so air is supplied to the boiler. Before entering the furnace, this heated in the air preheater to improve combustion efficiency.
The air preheater transfers heat from outgoing flue gas to incoming air. Notice the air and flue gas exchange heat, but they do not mix. When coal burns, it produces hot flue gases. But we don't waste their heat. The plant extracts useful heat from these gases before they reach the chimney. First, hot flue gas transfers heat to the superheater. The superheater raises the temperature of steam before it enters the turbine. Next, the flue gas passes through the economizer. It preheats the incoming feed water before that water enters the boiler. After giving up more heat in the economizer, the flue gas reaches the air preheater, where it heats the incoming combustion air. Finally, the remaining flue gases travel toward the chimney. In a real plant, emission control equipment helps reduce pollutants before discharge.
Coal doesn't completely disappear during combustion. The non-combustible residue becomes ash, which must be collected and handled safely.
The ash handling plant collects and transports the ash away from the boiler for storage, disposal, or possible beneficial use. The collected ash is finally transferred to ash storage. So our coal journey is complete. Coal enters and leaves the system mainly as ash and flue gas products. Now let's follow the second journey, the water and steam cycle. This continuous loop carries energy from the boiler to the turbine and back again. After leaving the turbine, exhaust steam enters the condenser. Cooling water removes its heat, turning the steam back into liquid water. The condensate extraction pump moves this water away from the condenser and sends it toward the feed water heating system. Next, the boiler feed pump raises the pressure of the feed water so it can be delivered into the high-pressure part of the boiler system. The high-pressure heater raises the feed water temperature further, improving the overall efficiency of the steam cycle.
The feed water now enters the economizer, where it receives recovered heat from flue gas before entering the boiler.
Inside the boiler, intense heat converts the feed water into steam. The steam then travels toward the superheater. The superheater adds more heat to the steam, producing high-temperature superheated steam. This steam is now ready to enter the turbine.
The superheated steam passes through the main steam valve, which controls the steam entering the turbine.
Inside the turbine, high-pressure steam expands through the blades. As it expands, it transfers its energy to the turbine shaft and makes it rotate. The rotating turbine shaft drives the generator. Inside the generator, a law of induction converts mechanical rotation into electrical energy. Now we need one more important flow, cooling water. It can come from a river, canal, or another cooling water source depending on the plant design.
The circulating water pump sends cooling water through the condenser. It absorbs heat from the exhaust steam and allows that steam to become water again.
And that's the complete story. Coal provides the heat, water becomes steam, the rotor of the turbine drives the generator, and cooling water brings the steam cycle back to the beginning. Remember these 4 paths. Coal creates heat, water carries steam energy, cooling water removes waste heat, and the turbine generator converts that energy into electricity. That's how a thermal power plant turns fuel into electrical power.
Now let's go inside the hydropower plant.
Can you believe that this moving water can light up entire cities? Let's discover how a hydropower plant turns the energy of water into electricity. Hydropower means generating electricity using the energy of moving or falling water, which rotates a turbine and ultimately produces electrical energy. One important concept is head, the useful difference in elevation that provides energy to the water. Generally, greater head and greater water flow mean greater hydropower potential.
A typical hydropower plant includes a reservoir or river intake, water conveyance system, tiny transformer, and a path that returns the water downstream.
The intake controls the water entering the plant, while gates regulate the amount of water moving toward the turbine. The penstock carries water from the higher reservoir toward the turbine. As the water descends, its potential energy is converted into air associated with the flowing water. Inside the turbine, the energy of flowing water is transferred to the runner. The runner rotates, converting hydraulic energy into mechanical energy. The turbine shaft drives the generator. The generator converts the turbine's mechanical rotation into electrical energy. Generate electricity passes through a transformer, where its voltage is efficient transmission over long distances. Then the power travels toward the electrical grid. After transferring energy to the turbine, the water leaves through the draft tube and flows into the tail race, eventually returning to the river. The first major type is the storage or impoundment plant. A dam stores a large quantity of water, although when and how much water is released for generation.
When electricity is required, stored water flows through the intake and penstock, rotates the turbine, drives the generator, and sends electricity to the grid.
The second type is run-of-river hydropower. Instead of relying on a large reservoir, it mainly uses the river's natural flow. With water is diverted through the plant, passes through the turbine, generates electricity, and returns to the river. Because storage is limited, output depends strongly on available river flow. The third type is pumped storage hydropower. It uses two reservoirs at elevations and can both generate electricity and store energy. During high electricity demand, water flows from the upper reservoir to the lower reservoir through the reversible turbine, generating electricity.
When electricity demand is low, the process reverses. Electricity powers the pump, which moves water back uphill into the upper reservoir, storing energy for later.
Hydropower plants also use different turbine designs. Three important examples are Pelton, Francis, and Kaplan turbines. Pelton turbines are commonly suited to high head applications. Francis turbines are widely used for medium head conditions. Kaplan turbines are designed for high flow, relatively low head applications. So remember, storage plants control stored water, run-of-river plants mainly use natural river flow, and pump storage plants store and generate energy. In every case, water drives the turbine drives the generator, and engineering turns water into electricity. The adventure isn't over yet. Subscribe to MindSpark Toons for more amazing stories, history, and learning adventures. See you next time.
Now let's study nuclear power plant.
Imagine an energy source hidden inside the tiny nucleus of an atom, producing enough heat to generate electricity for an entire city. But how does it work? Let's step inside a nuclear power plant.
A nuclear power plant is essentially a thermal power plant where nuclear energy provides the heat. That heat produces steam. Steam rotates a turbine, and the turbine drives a generator.
The main source of heat is nuclear fission. When a suitable heavy nucleus, such as uranium-235, absorbs a neutron, it can split and release energy along with additional neutrons.
The released neutrons can trigger more fissions. This creates a chain reaction, but inside a power reactor, that reaction is carefully controlled.
At the heart of the plant is the reactor core. It contains fuel assemblies where fission occurs and produces enormous amounts of heat. The reactor fuel is arranged in fuel rods and fuel assemblies. Inside the rods are fuel pellets containing nuclear material surrounded by protective cladding.
Control rods absorb neutrons. By adjusting their position, operators and automated systems can control reactor power and help shut down the chain reaction when required.
The reactor doesn't send nuclear energy directly to the turbine. A coolant carries heat away from the reactor core and transfers that heat to another water system. Let's use a pressurized water reactor, or PWR, as our example. The primary water is maintained at high pressure and transfers heat to a separate secondary system. Let's trace the loops. The steam generator is a heat exchanger. Heat passes from the primary coolant through tubes into the secondary water, producing steam. This steam now carries useful thermal energy. It travels through the steam flow toward the turbine, where its energy will be converted into rotation. As steam expands through the turbine stages, it transfers energy to the blades. The turbine shaft begins rotating at high speed. The rotating turbine shaft drives the generator. Through reduction, mechanical rotation is converted into electrical energy. The generated electricity passes through transformers, where its voltage is increased for efficient transmission through the electrical grid. After leaving the turbine, the steam enters the condenser. Cooling water removes its heat and converts the steam back into liquid water. The condenser needs cooling. Depending on the plant design, heat may be rejected through cooling towers or another cooling water system. The condensed water is pumped through the feed water system and returned to the steam generator. The steam water cycle is now complete. So our complete energy journey is: nuclear fission produces heat, heat produces steam, steam rotates the turbine, and the generator produces electricity. Here's an interesting point. Nuclear and coal plants both use heat to produce steam. The major difference is the source of that heat: combustion in coal plants and nuclear fission in nuclear plants. Nuclear safety uses multiple layers of protection. The fuel, cladding, reactor coolant boundary, reactor soil, and containment structure form important physical barriers.
Operators continuously monitor important parameters such as temperature, pressure, neutron behavior, and cooling system conditions. Nuclear plants also have safety systems designed to maintain essential cooling and control conditions during abnormal situations.
If necessary, the reactor can be shut down by rapidly inserting neutron-absorbing control elements. But even after shutdown, the fuel continues producing some decay heat, which must be managed.
Now let's discuss radioactive waste. Radioactive materials require controlled management, and different types of waste require different treatment, storage, and disposal methods.
Lower activity radioactive waste can include contaminated clothing, filters, tools, and other materials. It is sorted, treated, or conditioned when appropriate, packaged and managed at licensed facilities. Spent nuclear fuel is different. When removed from the reactor, it remains highly radioactive and continues producing heat, so it requires specialized cooling and shielding. Spent fuel can initially be stored in specially designed pools. The water provides both cooling and significant radiation shielding.
After sufficient cooling, spent fuel can be transferred to dry storage systems where appropriate. These systems provide shielding, containment, and passive heat removal.
Some countries choose reprocessing. In that approach, certain usable materials can be recovered from spent fuel for possible recycling. But radioactive waste still remains and requires controlled management. Before long-term disposal, radioactive waste may be conditioned into stable forms and placed into specially designed packages that provide containment.
For material designated for disposal, one major long-term concept is deep geological disposal, placing conditioned waste deep underground in a carefully selected geological environment. The key idea is multiple barriers. The waste form, container, engineered barriers, and surrounding geology work together to isolate radioactive material from people and the environment.
Radioactivity decreases naturally through radioactive decay. Different radionuclides have different half-lives, so some remain significant for much longer than others.
Radioactive waste cannot simply be treated like ordinary garbage. Its management must account for radiation, heat, material properties, containment, and long-term safety.
Nuclear facilities also use monitoring systems to check radiational environmental conditions, helping demonstrate that safety requirements are being maintained.
Nuclear power is one part of a larger electricity system. Engineers can combine nuclear generation with renewable sources, storage, and other technologies to meet changing electricity demand.
A nuclear plant can provide a large amount of steady electricity, while other resources and technologies can help manage changing demand and variable generation. Let's zoom out and see the complete plant. Every major system has a specific job, but together they form one continuous energy conversion system. Remember the chain. Nuclear fission produces heat, heat produces mechanical rotation, and the generator converts that rotation into electricity.
The fuel cycle also continues after electricity generation. Spent fuel is cooled and stored, and depending on national policy, it may be reprocessing or managed for long-term disposal. 3 simple words can help us remember the safety philosophy: control the reaction, remove heat, and contain radioactive material.
Nuclear engineering is not only about producing energy, it is also about safety, reliability, environmental protection, careful fuel management, and responsible waste management. From a microscopic nuclear reaction to electricity flowing through transmission lines, every stage is carefully engineered and interconnected.
For waste management, lower activity wastes follow appropriate licensed disposal pathways, while spent fuel requires specialized storage and, where designated for disposal, a carefully engineered long-term solution. The real achievement isn't simply splitting an atom. It's controlling the energy safely and converting it into reliable electricity that supports modern life.
Quick challenge! What actually rotates the generator? The reactor, the turbine, or the cooling tower? Think about it! The answer is the turbine! Steam rotates the turbine drives the generator, and the generator produces electricity. From the nucleus of an atom to the lights in your home, that is the incredible journey of nuclear energy. Keep questioning, keep exploring, and I'll see you in our next energy adventure. The adventure isn't over yet. Subscribe to MindSpark Toons for more amazing stories, history, and learning adventures. See you next time. The adventure isn't over yet. Subscribe to MindSpark Toons for more amazing stories, history, and learning adventures. See you next time.